This first presentation is basically just an introduction to cathodic protection, and it's intended for just anybody who wants a basic understanding of what cathodic protection is, and really as an orientation for MatCor employees to get a good, firm understanding of what MatCor does. And I want to start just by saying, what is cathodic protection? And for the next 60 minutes or so, we're going to be talking about what cathodic protection is and how it works. And quite simply, the definition of cathodic protection is it's a means to prevent corrosion of metals. Okay? It's not the only means to prevent corrosion, but it's a means to prevent corrosion. And it's a means to prevent corrosion of metals by using electrical current. Okay? And if we can use electrical DC current properly applied, it will stop the corrosion reaction completely. So if cathodic protection is done correctly, it will completely stop corrosion. Another thing that's important to note is some cathodic protection will slow down corrosion. So in theory, if somebody says, I only have this asset and I only want it to last 20 years, they don't need a full 100% cathodic protection solution. They may be able to get away with less than 100% cathodic protection solution. So what is corrosion? And as you can see from this slide here, corrosion is it's a reaction. And with very few exceptions, all metals take a lot of energy to put into them to be able to use them. Okay, you don't go out and you find a carbon steel piece of rebar. What you mine is you mine iron oxide, and you have to turn that iron oxide into a metal that you can use. And that's true for basically every metal. There are a few exceptions. Gold, silver are the two notable exceptions. Gold, you actually find gold as gold. But almost every other metal in nature is found as an oxide and has to be processed. And that processing is a process of putting a lot of energy into metal. Well, that's not natural. Nature wants to take that energy back out. Okay? So if you take a metal that's been refined in a steel mill or a refinery, its natural state has been changed. You've bottled a lot of energy into that metal. Corrosion is just the process of nature taking that energy back out. And that's a picture of a rusty old car. That's what happens when processed metals are left out in the environment long enough. They'll return to a more natural state, in this case, iron oxide or rust. It's the process of energy leaking out. So again, cathodic protection is a means to stop that energy from leaking out of the structure. So how does it work? The corrosion reaction basically is what we call a oxidation reduction reaction. It's a chemical reaction where the metal reacts with the environment to reduce it to an oxide form, a metal oxide form. And if you look at it at a micro level, what you see here is one side of this structure, and this could be the wall of a tank bottom, for example, or it could be the surface of that car we just saw, the rusty surface of the car. One section of that structure is what we call anodic. It's slightly less negative electrically than the next section. And that current then will flow from that anodic section to the more positive section, the cathodic area. And corrosion occurs where that current leaves the structure. Okay, we call this a corrosion cell or a galvanic corrosion cell. And this is what happens in nature. And if you look at that rusty old car, you'll see there's rust spots and there's spots where there's no rust. Now over time that moves, and eventually the whole thing turns to rust, to the point where you can stick your finger through the fender of a rusty old car. But this is happening on a micro level throughout that whole structure. Current leaving in one area, and where it leaves, that's the corrosion reaction, and current landing in another area. And that's
where it lands is not corroding?
Where it lands, there's no corrosion going on, at least at that time. Now later, current might discharge off here and move somewhere else because the reaction keeps going. And as the electrical chemical properties change, it moves where the reaction occurs. But if you ever look at something that's rusty, it won't be just homogeneous rust. It'll be rusty spots here and there, and there'll be spots that aren't rusty. Now, if you leave it long enough, the rusty spots will start to migrate and move. That reaction will start to migrate and move. There's 4 elements to that little micro corrosion cell that I showed. And it's real easy if you live up here in the Northeast to remember that, because we have Acme grocery stores. And if those of you who are cartoon buffs, you remember the Acme Roadrunner and the Acme brand dynamite. So that's the acronym you need to remember for what a corrosion cell is. It's ACME. Anode, a cathode, a metallic path, and an electrolyte. And I'll go through what each of those mean. But if you can eliminate any one of those four, you'll stop that corrosion reaction. So let's go back to our slide here. Actually, let me go back to the previous slide here. My anode, my cathode, and my metallic path. The structure itself provides that. It's inherent in a piece of metal. It already has an anode, it already has a cathode, and already has a metallic path. All you really need is this electrolyte. An electrolyte is a fancy word for saying something where current can flow. And in most cases, that's water. In soil, in the atmosphere, that rusty car we looked at, that rusty car, all it needs is a thin film of condensation to create an environment where corrosion can occur. If you take and you bury a steel coin and you go back and look for it 100 years later, the steel coin's gone because it will have dissolved. There's enough water or moisture in the soil to provide as electrolyte. It doesn't have to be water as an electrolyte. Yes, Knut?
Conversely, if you put a car somewhere into the Sahara Desert where it's extremely dry,
The corrosion rate is virtually zero.
so it would still be there 100 years.
And in fact, if you took a car and put it on the moon, there is no electrolyte. So, in fact, if mankind were to be wiped off the face of the earth tomorrow, the last vestiges of humankind would probably be the flag on the moon because it will never corrode and it'll never go away. It just sits there. So yes, if you have no electrolyte, there's no corrosion. Okay. Unfortunately, here on Earth, there's corrosion, and the hotter it is, the warmer it is, the more humid it is, the faster the corrosion rate is going to always be. So, if you get nothing else out of this presentation, if you can just embed this picture in your mind, this is how cathodic protection works. Everything else is details. Basically, the way cathodic protection works is we take an anode. This is an external device. We place it in the electrolyte and create a circuit where current flows from the anode that we put into the circuit through the electrolyte to the surface of the structure. Remember I said where current lands, there's no corrosion? And where current discharges is where the corrosion occurs? We're moving the corrosion to this anode. Okay? So by putting current onto the structure, flowing electrons onto the structure, we've moved the corrosion. Now, I intentionally made this slide to show a little bit of corrosion, okay? Because what I want to show is you're not putting metal back. So if we take a structure that's been out there for 10 or 15 years in the field and we put cathodic protection on it, it's not going to be returned back to its original state. All we do is stop the corrosion from occurring any further. Okay?
But in that theory, does the anode eventually corrode?
Well, eventually the anode has a life. And if it's not putting out enough current, and we'll talk about how much is enough current, and all those are details. Just keep in mind, current flowing from the anode through the electrolyte to the surface of the structure we're trying to protect will protect the surface from rusting or corroding. Okay? One other comment here. If the structure is in such bad condition that it's mostly rust and very little meat left, very little solid metal, and you put cathodic protection on it, it could still fail. Okay? So if somebody were to come to us and say, I've got this above ground storage tank and I'm worried about my tank bottom that's in contact with soil and I'm worried about the corrosion of that tank bottom and the tank leaking, very common application for cathodic protection, and you talk to them and you find out that that tank's 22 years old and that they did a survey of the floor of the tank and they found that it got 80-90% corrosion, putting CP on it probably won't keep it from leaking. In fact, it might actually encourage leaking because what does happen is as you flow current onto there, that rust particles will start to be pushed away a little bit, and now all you've got left is nothing but a real thin piece of metal maybe. So that's one caveat there, is if the structure is in such bad shape that even if you stop the corrosion from occurring any further, it's already gone. Okay, so at some point, you're better to repair it, put CP on it, and have it last forever from that point. But if you get a structure that's had some minor corrosion, and you put CP on it, you'll stop the corrosion, and you'll maintain the life of that structure for as long as the CP system's properly operating. That's a great question. I'll repeat that. If this was the wall of a pipe, and the corrosion's on the outside of the pipe, does the cathodic protection protect the inside of the pipe? And the answer is no. Okay? Cathodic protection only works by stopping current from leaving the structure by putting current onto the surface of the structure. Okay, and I'll talk about some analogies here to help you visualize that process. But I can't put current on the inside of the pipe unless I have the anode in the pipe. And we actually have a product for that, for certain applications, where you can actually have anodes inside the pipe that throw current to the inside of the pipe to protect from internal corrosion. Yes, Knut.
Building on that, what happens to the other side of the pipe?
Now, if you're talking about a pipe in the ground and you've got an anode source, current doesn't flow exactly straight line. Current will flow in around the whole pipe. So you can protect the entire exterior of the pipe from an anode that's remote as long as the anode's far enough away. And I'll talk about that when we get into distribution, current distribution. But current will actually flow around something as opposed to a light where if you put something in front of the light won't go beyond it. And talking about light, that brings me to my next analogy. A lot of people have a really hard time visualizing electricity. You can't really see it, okay? And so electrical discussions, it's hard for people to conceptualize. It's hard for me to conceptualize sometimes. So I like to use analogies. And the first analogy I like to use is light. If I can light up the surface of a structure with current, I can stop it from corroding. Okay, so a lot of times when I think about cathodic protection, I think of how do I light up the structure? And my anodes are my light source. Okay, so clearly if you take a light bulb or a flashlight and you put it really close to a wall, you're only going to light up a small area of the wall. If you move it back, you're going to light up more. Okay, that's a useful analogy in cathodic protection. It's not a perfect analogy because I said current will flow around things, but it's a good analogy to consider. So I use the light analogy. I'll talk about lighting up a structure. Okay, and then the question just becomes, can I get the light distributed everywhere, and can I get enough light? Because there's a certain threshold. Once you get a certain amount of light, it's not corroding anymore. Okay, some light that's below that threshold will slow down the corrosion rate. Any light is good light, to use that analogy. Another analogy I like to use is the stadium analogy. And in the stadium analogy, again, we talked about electrons flowing onto the surface. Corrosion, the term oxidation reduction reaction, if you're a chemistry person, is basically, you talk about losing electrons, losing positive charges as part of that reaction. Okay? Losing negative charges, excuse me. So if you can bombard the surface with electrons, the structure can't give up electrons. Okay? Because that's what metals want to do. They want to give up electrons and react with the environment and create rust. Okay? So if you're bombarding the surface with electrons, you can't give up electrons. Just like trying to walk into a very crowded stadium at the end of a game when everybody's leaving. Okay? It's really hard to get in because everybody's leaving. Well, the same thing is true with the reaction for corrosion. If I'm bombarding the surface with electrons, the electrons can't leave the surface. So let's take a look at a pipeline example. Here's a pipeline with no cathodic protection on it. Okay, and as you see along the pipeline, typically buried steel has a potential somewhere around minus 550 millivolts. Okay, it varies a little bit. It might be a little more, it might be a little less. And if you took a bare pipeline and you put it in the ground, you would find there's variations along that pipeline, naturally occurring, because the steel is not exactly the same everywhere. The soil environment is not exactly the same everywhere. So there'll be minor differences in the potential. Well, everywhere you go from a minor positive to a minor negative, you've created a current flow. Okay? So along this pipeline, you have all these little micro cells where galvanic corrosion will occur. We call that galvanic corrosion. So if there's no cathodic protection on a bare pipeline, you're going to start corrosion. Now, in real life, we don't put a lot of bare pipelines in. We typically will coat the pipelines. All that does is provide a barrier so that the pipe steel is no longer in touch with the environment. But no coating is perfect. So even if it was coated pipeline, you'd still have this phenomenon. It would just be at those areas where the coating wasn't perfect. But if you put cathodic protection on that pipeline, and I now have an anode like Matcore's linear anode, for example, okay, and I run that parallel to the pipeline, and I'm discharging current off the pipeline, or off the anode onto the pipeline, I'm lighting that pipeline up, I'm flowing electrons onto that pipeline, I'll stop the corrosion. And what happens is the entire steel structure will become more negative, because if you're throwing negative charges onto a structure, you're going to do something what we call polarize. Okay? And we talk about polarization quite a bit in cathodic protection. Polarization just means I'm making it more negative by showering electrons out. Now you stop the shower of electrons, it'll go back to its normal or native state. But as long as you're throwing electrons onto it, I kind of like visualize that as like if you were a Star Trek person, you got your shields up. When we put cathodic, when we turn that power supply on, we start flowing current on, we're putting a shield onto that pipeline. And as long as the shields are up, as long as the power is going, that pipeline is not going to corrode. And that's what we're doing here. So you now see this pipeline has gone from being minus 550 to minus 560, minus 580, with all these little micro differences in potential. I'm showering the whole thing with so much current that now all of a sudden the whole thing is at minus 1,000. Okay? And there's no way current's going to discharge off that pipe because it's got current flowing onto it. Which gets me to my next slide. This is a slide that shows corrosion rate versus applied current. So this is me lighting up that structure. And you see the corrosion rate goes basically to zero. The corrosion rate never goes to exactly 100% zero, but it gets so low that 1,000 years from now you wouldn't even be able to notice the difference. Okay? As long as the CP system ran the whole 1,000 years and they kept replacing the CP system and putting new ones in because they don't last that long. 25, 30 years is reasonable for a corrosion system. But you can see the corrosion rate drops as we start to apply current. Now for some metals, and we get into detailed design and talk about specific applications, we do worry about this occasionally. For some metals, there reaches a point where you start applying too much current and you can actually cause damage to the metal. Okay? So that's this sign over here where I start showing the corrosion rate starts to increase at some point if you're starting to apply too much current. But the goal is to apply enough current to get that corrosion rate down to where it's functionally zero. At that point, we say it's cathodically protected. And we use the term criteria. What constitutes enough cathodic protection? At what point do I have enough light on the structure that that corrosion rate is effectively zero? Okay? There's several criteria that we use for corrosion cathodic protection. There's international criteria, there's criteria in the US, Canada, and the United States use basically the same type of criteria. There's an organization called NACE. In the corrosion world, NACE is the International Corrosion Society. It used to be the National Association of Corrosion Engineers, but they've gone global and they don't like to be called national anymore. So they just go by NACE. But NACE has defined 3 criteria, and actually the first 2 are basically the same. There's something called 850 on, 850 off. Remember I said that this natural potential of steel when it's buried generally is around minus 550 millivolts? If you can shift it to being negative 850, remember I said as you throw current onto it, it becomes more negative? If you can shift it to negative 850, it's protected, okay? And we use on and off. Basically they're the same. On means that when you have the CP system on, it's negative 850. Off means the minute you turn it off, it's still at negative 850, okay? And there's some technical issues about what the difference is between them, but for the purpose of this discussion, let's just say they're basically the same criteria, negative 850. The other criteria is 100 millivolt shift. If you can get 100 millivolts of polarization from its native state to its state when it's cathodically protected, you'll stop that corrosion rate. Now you'll say 550 to 850, that's more than 100 millivolts. That's true. But the 550 is just a general state, okay? Sometimes steel and buried steel could be minus 600, minus 700. The 100 millivolt shift means you have to actually test it before you put the CP on, have a native state potential, and then you're going to compare that to a protected potential. So both are used quite a bit in the industry, but the key concept there is, how do I know how I have enough light, okay, to light up the structure? We talked about too much current. Overprotection can have some adverse effects. This is especially true on certain metals like stainless steels, titanium, exotic metals. Carbon steel, it's virtually impossible to put too much current on it. But there's a practical issue there too. At some point, you're just wasting current. Once it's protected, why throw a lot more juice onto it? Why put a lot more light onto it? Okay. So while it is pretty immune to over current or putting too much current on it, there's a practical aspect of why would you do that? It doesn't make sense to put too much current onto it. Usually at this point of the presentation, I ask everybody, do you have a cathodic protection system in your house? Now those of you who have heard me ask that question, don't raise your hand, but just for grins. Carlos, do you know, you're new here, do you know if you have a cathodic protection system in your house?
No, not actually.
Oh, okay.
Is it a water heater?
Exactly. Inside of almost every water heater, there is a cathodic protection system because the water that circulates in a boiler or a water heater is pretty corrosive water. And they make those water heater tanks out of carbon steel, and they put an anode inside there, and the anode will protect that carbon steel for as long as the anode lasts. And the really cool thing is they actually can calculate how long they think that anode's going to last, and they base their warranty on that. So if you go to Home Depot and you buy a 10-year warranty hot water heater, that anode decides to last about 10 years, actually a little less than 10 years because they know it's going to take some time for the corrosion to cause a failure. And if you go and buy one that's got a 20-year life, it's got a bigger anode inside. And if you buy a commercial water heater, they actually have a threaded connection, and you can actually replace the anode because they know that they're more expensive. The clients are going to replace those anodes as a maintenance basis, and in theory, that water heater should last as long as they keep replacing the anodes. So I want to talk about some of the basic CP system components. Now that you understand how cathodic protection works, what do we do to make it work? What do we need? Obviously, we need something to protect. We need a structure we're going to protect. We protect lots of different structures, and when we talk about designing CP systems a little later, we're going to ask questions about the structure, but you need something to protect. You need an electrolyte. Got a call the other day from a client in Brazil, actually, and they were doing offshore windmills to generate electricity. And they wanted to protect the fans on the windmill because it's a corrosive, saline seawater environment. And I said, well, you know, we can't put cathodic protection on the blades of your windmills because there's no electrolyte there. Yes, you're going to get seawater spray onto them and it's going to cause corrosion issues, but I can't put an anode in the electrolyte to flow current through the electrolyte to protect the steel. So they had to go with some other type of corrosion protection. We don't do well with atmospheric applications because the air does not allow the conduction of electricity. But we're great if you've got something in water, seawater, or soil. And most of our applications are in those 3 electrolytes, or 2 electrolytes. The other one is concrete. We actually can protect metal and concrete like reinforcing steel. So you need a structure to protect. You need an electrolyte that current can flow through. Obviously, you need some sort of an anode to deliver current. These are my lights that are going to light up the structure. And then there's some cabling in there to connect it because you have to have that metallic path or that circuit, okay? So you have to have something connecting the anode to the structure. Often there's multiple connections of the anode to the structure. And then finally, I always emphasize this with people, you need provisions for testing it because if you're going to put a cathodic protection system in, you want to be able to make sure that it's working properly and testing it. So we put provisions for testing. And just from a schematic standpoint, here the orange color is the electrical current flow, and you can see it's just a big circle. Okay, if you have a rectifier or power supply, current flows off the power supply through the cabling system. There may be junction boxes connecting the cables to the anode system, through the electrolyte, to the structure, back through cables, back to the rectifier. It's a circuit. Now, if you were to cut those cables, it's an open circuit and current will flow, just like in your house. If you cut the cables to your lights aren't going to turn on, okay? So that's the basic schematic of what a CP system looks. Now, we have all different flavors of structures. We protect tanks, we protect seawalls, we protect jetties, we protect pipelines. There's all different types of anodes, but that's basically how the system looks from an overview.
So the rectifier is the power generator.
And in some cases, there is no rectifier. And I'll talk about that in a few minutes about galvanic systems where we actually are using a system that doesn't need a power supply. But in many cases, a power supply is needed especially for larger structures or structures that you want to have a longer life on them. So let's just go through a quick example of a cathodic protection system, okay? A real world actual application. Here what you see, this is a very common in any type of near shore or on the shore facility. It's called a seawall. Basically they're taking sheet pile, this is metal sheets, they pound them into the ground, okay? And that separates the water from the land side. The nice thing about that is now you can dredge that area, and now you have an area you can bring boats up, and then you can make that pretty deep even. So if you've got a LNG terminal where you're going to bring in large LNG tankers, you know, you're not going to just run those up to the shore and have them hit the sand. You've got to create a channel, a deep channel, where you can berth the LNG tanker. Seawalls are very common to do that. So what you see here is a typical seawall. And if you can see it closely, you can see there's a little bit of rust on the atmospheric side of the seawall. Okay? Rust is an interesting thing because for certain steel structures, rust becomes a coating, and it kind of slows down the corrosion after that. Okay? You could also paint that. But what the bigger concern for this structure is what's happening in the soil side and what's happening where it's buried and in the water. We've got this seawall structure, okay? There's actually a couple of places we're concerned about. There's the land side of the seawall where the sheet pile is driven into the land and you have soil side corrosion, okay? There's the very bottom of the sheet pile, which is in soil on both sides because it's below the water level. And then there's that area where the water is, okay? There's also a small area where there's the atmosphere and its tides go up and down. That could change in its height, okay? That's the area you can, one, visually inspect, and it's easiest to get to repair if you were to have corrosion. And two, you can paint that, or in many cases, the iron oxide actually becomes a coating in effect. The rust, you'll get a thin layer of rust, and that actually becomes a coating. And that's very common in the type of steel that they're using for these sheet piles. But you can't inspect the land side. It'd be very difficult to visually inspect the land side for corrosion. And you certainly can't do anything, it's very difficult on the water side. The other thing is, a lot of times with these structures, is if they start to fall apart, it can be very difficult to get in and effect repairs to them. So cathodic protection is very commonly applied to these type structures. And one way to do that is with what we call a deep anode system or a deep well system. I'll discuss that a little more in this presentation. But as you can see here, I've got current flowing from my anode source to the soil side and hopefully up into the water side, protecting that whole structure from one large system. Okay? So that's a very typical and common cathodic protection system. The heart of any CP system is the anode system itself. Okay? And there are two types of anodes. There's galvanic anodes, often referred to as sacrificial anodes. So if you hear someone say sacrificial anode, they're referring to a galvanic anode. It's not the correct term technically. And in fact, all anodes have a finite life. Okay, there's no anode that has an infinite life. So all anodes, in effect, sacrifice themselves to protect the structure they're trying to protect, and at the end of their life, they have to be replaced. But the galvanic anodes have no power supply associated with them. And I'll talk about that in just a second. The impressed current anodes, and that's what mostly we manufacture, that's what we manufacture here at MatCor, is impressed current anode systems. Impressed current anode systems have power supplies, okay? There's pros and cons to each, and we're going to go through that in just a minute. But again, galvanic or sacrificial, no external power supply. Impressed current, you can put as big a power supply on them as the system warrants. This chart here shows what's called the electropotential of common metals, and in this case buried in soil. And what you'll see here is magnesium, aluminum, and zinc are naturally more negative than steel. Okay? I'll also point out that copper is much more positive than steel. And if you'll notice, silver, gold, and platinum actually are positive metals. We call those noble metals. They don't corrode. If you took a gold coin and you buried it in the soil, and archaeologists come around 2,000 years later, they're going to find that gold coin. If you took a steel coin and you buried it, 500 years later, you're probably not going to find anything. Okay, it'll have completely rusted away and dissolved into the soil. Okay. Magnesium is more negative, would have a tendency to consume even faster. If you couple magnesium to steel, okay, current flows from the more negative to the more positive. Current will flow off the magnesium, where current leaves the metals where corrosion occurs. So magnesium will consume or sacrifice itself in this galvanic reaction. Okay? But current will flow from the magnesium to the steel. How much current will flow? That's going to be a function of what the resistance is. The voltage difference is fixed. Magnesium has a natural potential. Steel has a certain potential. Now remember, when we flow current to it, the steel's potential is going to change. It's going to polarize. It's going to become more negative. So that difference in voltage potential, we call that driving force. Okay? That's how much we can push current off that magnesium. So the advantages of a galvanic anode system, and a lot of people will come to us and say, I want a CP system, I want one of those galvanic systems, or I want one of those sacrificial systems because I don't want to put a power supply in. Okay, great, we can do that, maybe, if it works right. But we're very limited because we have a very small driving force, less than 1 volt, between magnesium and polarized steel. Okay, so it's less than 1 volt. Whereas with the power supply, many of the power supplies we supply are 40, 50, 60 volts. Magnitudes of order more driving force to get more current out. Because remember, I talked about lighting up the structure with enough light to polarize it. But there are applications where magnesium anodes work just great. You take a bunch of these, and typically they come in cast ingots of hunks of metal, basically. 32-pound magnesium anode, very common in our industry. So you take a 32-pound magnesium anode, you bury it next to the thing you're trying to protect, you run a wire over to it, you connect them so you have a circuit, and that 32-pound mag anode will start to consume and start to flow current onto the steel as best it can. If everything works out great, it'll work. Some cases it's just not enough, or you need too many of them. So galvanic anodes, no need for power. In many cases they're lower cost because you don't have to have a power supply, and in theory little or no maintenance.
But you have to physically connect.
They have to be physically connected.
Cable from the pipe to that piece of magnesium.
Yes, the magnesium has to be connected to the pipe.
Oh.
Often they do it through a test station, so you can actually measure how much current's flowing off it. That's the only really way to know if the anode's still working or not.
Right.
Well, it's not the only way to know. It's the easiest way to know. It's also the easiest way to estimate how long the anode life will be, because we know how much the magnesium will consume for every amp of current discharged off it. So those anodes, it's just like a light bulb's rated for so many kilowatt hours. An anode is rated for so many amp hours. So if you know it's doing 200 millivolts, or 200 milliamps, excuse me, when you measure it, you can calculate how long it's going to last based on how much weight it has. The disadvantages of galvanic anodes: very low output, small driving force, low output. I call them Goldilocks anodes. They only work when the temperature, remember Goldilocks story, the porridge is too hot, the porridge is too cold? Galvanic anodes only work when the circumstances line up perfectly. If the soil resistivity is too low, meaning the current's going to flow too fast, those anodes will consume too fast. If the resistivity is too high, you're not going to get enough current off of them to protect anything. Okay? If the structure's too big and needs too much current, they're not going to work because you're going to need too many of them. You may end up putting in thousands of pounds of these, and it's not cost effective anymore. Okay? So I call them Goldilocks anodes, and I think it's important when we talk to people about CP that we make sure they understand that there's no free lunch. Yes, you don't need a power supply, but they are limited to where they work and work well, and that's where an expert can come in and look at it. They tend to have shorter anode life. I don't have a lot of choices for what anode material it is. There's those 3 metals, magnesium, aluminum, zinc, that are more negative than steel. I can't use anything else. Okay? There's no power switch. So once I install that anode, it's going to start discharging current based on the resistance in the soil and V equals IR. Talk about that in a little bit. But there's no adjustment. Okay? I put it in, it starts working. Really don't have a lot of way of controlling it. So if I didn't do the design quite right, or if the design was based on some flawed data, and you put it in, there's no real adjustment. With an impressed current system with a rectifier and a power supply, I have a switch. I can turn up the power, I can turn down the power. Okay, so there's a disadvantage there with that. Beware copper grounding systems. If you remember, copper was like minus 200 on that chart, meaning it's much more negative, or much more positive. When you have copper and steel mixed together in a structure, or if there's a piece of a pipeline and there's a copper grounding system nearby, and they're electrically connected, that anode's going to try to protect the copper first, because there's a bigger driving force. It's more positive, so it's going to try to bring it up to where it's the same potential as steel before current's going to start flowing to the steel quite a bit. What ends up happening with galvanic anodes is they can never protect the copper fast enough. Copper just sucks up current. That's what copper does. It's a grounding system, and copper takes current really quickly. It takes a lot of current to shift the potential of copper, a lot more current than steel. So you got to be aware of copper grounding systems, and it's much harder to test. I don't have a power supply, so I can't go to the power supply and measure things. So galvanic anode systems tend to be harder to test. There's a misconception, I think, with a lot of people in various industries that the galvanic systems are, because I have no power supply, there's no maintenance. But I make the argument that it's also harder to test, and you really never have that confidence level. If I have a power supply, I can have somebody go by the power supply once a month, look at the panel and say, yep, it's still kicking out current, still kicking out volts and amps, nothing's changed, it's still working. The galvanic anode system is buried, the pipeline is buried, it's forgotten about 5 years later and nobody's testing. In fact, I got a call yesterday from a guy. He's got a pipeline protected with galvanic anodes. I asked him, have you had it tested? He says, no. Do you know it's working? No. Now, if he had a rectifier and a power supply, he could look at the power supply and say, yep, it's still working, it's still working. Yes?
Wouldn't if you build a test station into the galvanic anode, wouldn't that take care of that?
You could put test facilities in for galvanic anode systems, and when we design galvanic anode systems, we do that, but it does require some level of sophistication to test it above and beyond just looking at a power supply and saying, yes, it's still where it was last month. Okay? So with those systems, you do require a little more sophistication in testing them. But yes, we do, definitely, I mentioned earlier in components, you want to have provisions for testing. But generally, they run until they're consumed, and then they fail. Let's talk about impressed current anodes a little bit. There's what I call conventional anodes. And the next few slides are conventional anodes. These tend to be very large anodes. They consume at relatively fast rates. Okay, so we're talking about pounds per ampere. So you still need a pretty large anode to generate a lot of current. The first one is what we call a graphite anode. That's literally a piece of graphite that has a cable connection to it, and you stick it in the ground and you run current off it. It consumes at a rate of about 2 pounds per ampere. And you can generate about half an amp per square foot of surface area. Okay? The next generation of anodes we started using was in the 1950s. They started coming out with these high silicon cast iron anodes. And back before that even, they would take old railroad ties. They'd hook them in the ground, put a power supply to them, and kick current off the railroad ties. But they came out with a formulation called high silicon cast iron. It's a special formulation used in anode production of cast iron, still in use today, quite common. High silicon cast iron anodes, they're hunks or cylinders of cast iron. They consume at a rate of about 1 pound per ampere, so it's a little bit better than the graphite, twice as better as the graphite. And they can kick out twice as much current for the same square footage, about 1 amp per square foot. Then in the 1980s or 60s and then moving into the 1980s, we started using precious metal anodes. And these precious metal anodes, they're much smaller anodes, kick out a lot more current and have a lot longer life. Okay? These are real high-tech anodes. The first one was platinum. A lot of issues with platinum anodes. MatCore was at the forefront of using platinum anodes for a long time. I have a lot of experience with them. We still use them in some selected cases. Wide range of configurations. Basically, we're talking about a very thin layer of platinum, micron levels of platinum, over some sort of a substrate, some sort of a metal that holds the platinum on, the platinum adheres to, and they consume at a rate of about 15 micrograms per ampere, or milligrams per ampere. So a very low consumption, not talking pounds per ampere, now we're talking about milligrams per ampere. And they can kick out 10 amps per square foot as opposed to 1 or half an amp per square foot. So I can get a lot more current off of them. I can generate a lot more current off of a smaller anode package, and it'll last longer. And then we started with the mixed metal oxide anodes, wide range of configurations, and a wide range of configurations, and these have almost no consumption rate. And actually, mixed metal oxide anodes are a unique beast, and that's what MatCore does now. All of the anodes that we produce, with the exception of some of the platinum anodes we produce, are mixed metal oxide-based anodes. Mixed metal oxide actually is more of a catalyst than an anode. All the other anodes we talked about really give up or consume, physically consume. This is a dimensionally stable anode. It allows the corrosion reaction to occur, or allows current to just discharge off of it in the presence of a voltage gradient. So let me rephrase that again. If you have a voltage gradient, you have a power supply that's generating a voltage differential over that anode, it'll start kicking off current. Now, it's not actually it's not giving up of itself to kick off current like a conventional anode would, but it uses the environment to generate current. So it's a current generator. But it has a finite life. At some point, it ceases to work as an anode. Okay? But these things last a very long time. One of the reasons that MatCore has specialized in building mixed metal oxide anodes is because you get exceptionally long life, exceptionally high reliability, and you can generate large amounts of current from fairly small anodes. Well, that's the other thing. The anode, mixed metal oxide is actually a coating over a titanium substrate. So we take titanium metal. that metal can be in a wide range of configurations. And actually, one of my later slides, I talk about configurations. Unlike a cast iron anode, where basically you're casting a cylinder, a long rod, okay, and you can't really cast a lot of neat structures. We can cast mixed metal oxide, or we can coat mixed metal oxide on a wide range of structures: spheres, ribbons, wires. We do a lot of wire anode. We're using very thin wire coated with mixed metal oxide, rods, tubes, plates, mesh, chicken wire mesh, for example, that you can put on concrete. So there's a wide range of configurations that you can use mixed metal oxide in. Some of the other components in an anode system, I don't want to dwell on these, but these are part of it. We often use a backfill around the anode. And what a backfill is, it's a nice low resistance environment, because we're going to discharge current off the anode. It's nice if that current discharges into a nice low resistance environment. And what that does is it's like when you have a light bulb in your house. The light bulb is actually that filament element in an incandescent light bulb, but then there's a housing around it so that the light discharges really off that housing. Well, that's how the coke backfill works. The coke allows current to discharge evenly off the entire anode so that the anode wears evenly, and then it discharges from the coke into the soil. Another element, especially for impressed current systems, is the power supply. Obviously, with a galvanic system we talked about, where there's no power supply, you don't have a rectifier, but this is a common rectifier. Rectifiers come in all shapes and sizes. And it doesn't have to be an AC electricity generated power supply. Okay? Pipelines in remote areas where there's no electrical power, we can use a generator. A lot of these gas pipelines, they've got gas flowing through them anyway, or if you're at a wellhead site that doesn't have power, they've got a gas wellhead, but there's no AC power to it. Well, they're producing gas. They have natural gas. You could put a little generator there that burns the natural gas, creates electricity to run your CP system. Solar power with batteries. You get a solar power panel or several solar power panels tied to a battery system. The battery is DC power. You hook that up to your CP system. You're off and running with no electrical power. Electrical power is generally the cheapest way to go. When you start talking about solar power or thermoelectric generators that burn gas or some sort of fuel cell hybrid system, those start to get expensive. But if you don't have no power, that might be a way to go. Some other components, we talked about test stations to be able to monitor things. You see these little yellow pipes. If you're driving along a highway, you're going to see these little yellow pipes sticking up on the sides of the highways, especially if you see little signs that say gas pipeline. Those are test stations. That's an ability to go and touch or electrically connect to the pipe without having to dig it up. And you can see that right here in the center picture. The center picture, you see some wires connected to the pipeline. So when they're putting the pipeline in, they'll make attachments to the pipe so you can physically test the pipe without having to dig up the pipeline to make a connection to the pipe at that point. So those test stations, typically if they put a new pipeline in, they're going to put a test station every mile. That way every mile there's a place to connect to the pipeline. And then on the right-hand side, there's a reference electrode. Reference electrode is just a fixed potential that you could put that into shown there's a sack there. We make those here in our shop. You put that reference electrode, you bury it, you put it next to the metal structure. You have that lead wire coming up, you have the structure wire coming up. All of a sudden, right there above ground, all you have to do is take a voltmeter and you can measure the potential between the structure and the reference cell, which is a fixed known potential, and you can do your testing. That's how you can test to see if you're getting polarization. You can turn the CP system off, wait till it depolarizes completely. You can measure it. Then you can turn the CP system on, allow a little bit of time for it to polarize, go back and measure again. You can measure what that polarization is. Am I getting enough light to protect that structure? I'm going to get into a little bit of design theory here. This is not intended to make any of you designers of CP system, but just to give you an idea of what information we tend to look for and how we go about designing CP systems. Okay, so there's my legal disclaimer. Just because you sat here 10 minutes listening to me talk about design, don't do it at home. There's a couple of ways you can start. I always like to start with the structure we're trying to protect. That seawall application that we showed earlier, I showed the picture of that little seawall. What's the structure? What's its geometry? What's its size? Is it coated? Is it not coated? Is the coating brand new and really high quality? Because we have some great coatings today. Or is it put in the 1950s and the coating technology in the 1950s wasn't so good, plus it's now 40 or 50 years old coating. Okay, and coatings don't last forever, they degrade. So we ask questions about that. Is it electrically continuous? You have some structures that there may not be electrical continuity between different parts of it. Okay, ductile iron pipe systems are really bad for that because ductile iron pipe is there's a joint of pipe, 20-foot joint. It's got a little bell to it. The other end's got a gusset to it. They push them, pressure fit them together, and they put a gasket between them. Well, that gasket can cause electrical isolation, so you may not have continuity between one section and the other. That can be a really bad issue when you start putting cathodic protection on it, because what happens is you polarize one segment, but current's not flowing to the segment that's isolated because it's not part of the circuit, and now all of a sudden you have a major opportunity for current to flow off of your CP system onto the structure that's isolated and then back off again because it has to get back to the circuit. And where it goes back off, you can have corrosion. We call that interference. And you can actually cause corrosion very quickly if you do that.
What's the solution to that?
You have to have bonded structures, okay? Or, and in some cases, you may have to dig up the structure and put bonds in.
So what's a bond, some sort of link between?
Yeah, it's an electrical wire. They will attach to both sides of a piece of pipe,
Joint.
to a joint, yeah. With the seawall,
How would you know that?
you can test for continuity.
Oh, you can't.
Yeah, you can go to one end of the pipeline, go to the other end of the pipeline, run a wire between them and see if there's electrical continuity or not. We will do continuity testing on some structures. That seawall I showed, those are generally individual segments of sheet that are piled, driven into the ground and connected. Well, you want to make sure those connections are electrical. So we'll actually go out and we'll test to make sure there's electrical continuity. There again, it's pretty easy to bond across them. So there's some issues there. We want to know what metal it is. Remember I mentioned there's some metals that you don't want to put too much light onto because you can damage them. So we want to know what metal it is. Carbon steel, is there copper in the area? Or do we have to worry about copper? So there's a lot of questions we'll ask about the structure we're trying to protect. The second stage is to evaluate the environment. Okay? Around the structure. It says evaluate the structure. I need to fix that slide. I apologize. So we want to talk about the environment. What's around that structure? Okay? That sheet pile wall that we showed, okay, is that seawater or fresh water? Because if that's on a lake or a river where the water's fresh, that's a whole different animal than if it's in seawater. Is it in seawater up in the Northeast where the water's cold and there's not as much salt in it, or is it down in the Caribbean where it's warm all the time? Remember I mentioned temperature affects corrosion rates? It affects it significantly. Every 10 degrees Celsius increase in temperature doubles the corrosion rate. Okay, as a general rule of thumb. So corrosion rates can go up really quickly if you get into elevated temperatures. That's why things in hot temperatures always seem to be rusting a lot faster than things in colder temperatures. So there's a lot of questions we ask about the environment. Does the environment change or is it steady state? Okay. If you're MatCor, we're located here near Philadelphia. The Delaware River changes seasonally. In the summer, the salt line moves up the river, and you end up with very low resistance, very salty, corrosive water. In the winter, that salt line tends to move back towards the ocean, and you'll have a structure that will have being more fresh water, less corrosive, but also more difficult to flow current through because now the resistance of the water's changed a bit. So does the environment change over time? Is it seasonal? In some places, the soils can change radically just depending on whether it's wet season or dry season. So we ask questions about the environment. The final step to consider is anode placement. Are there constraints to where I can put the anode? Earlier I talked about a flashlight and putting it close to a wall and moving it back. Sometimes you can't move it back. Sometimes you're physically constrained into what I can do with where I can put anodes. Okay? If we're working on a gas well, the owner owns a 100-foot by 100-foot square plot where his gas well is, and around that's a farmer's field. Well, I put anodes in the farmer's field, and every spring he's running his tractor through there, and you know, I have to be careful how deep do I put the anodes, where do I put the wires. Will he even let me put anodes in his field? Maybe I have to put them in that 100-foot square well casing that the operators leased from the field. So there's all kinds of questions about where can I put anodes, because that'll constrain my design. So after I've asked my questions about what's the structure, what's the environment around the structure, and what's the constraints for what kind of anodes I can use, now I can start thinking about designing. The first thing we do when we design a CP system is we try to evaluate how much current I'm going to need. Okay, we talk about lighting up the structure and putting enough light on the structure to light it up. How much light do I need? We can run some calculations on that. Okay, so there's theoretical calculations that we can run to determine how much light I need. Another way to do it is to go out in the field and test it. Okay, I take a portable or take a portable power supply. I drive an anode into the ground or a stake into the ground. I run current off of it. I measure how much shift I get to the structure. We call that a current demand test. Let's say I put 2 amps of current off this, and we can use a car battery for that. We actually have done that. We'll take a car battery, we'll put a stake in the ground, we'll hook the car battery up, we'll put a voltmeter on the structure, we'll say, oh, the structure shifted 15 millivolts or 20 millivolts. Based on that, I can extrapolate how much current I need to shift at 100 millivolts. Okay, so that's called a current demand test. Sometimes current demand tests work great. Many times we just estimate. Okay, we know that if we put so much current per square foot of surface area onto a carbon steel structure, that we're going to get enough polarization.
Is it the surface area of the structure you're trying to?
The surface area structure is the biggest issue.
What are you trying to
Yeah.
protect?
Yes, of what we're trying to protect. So I'll give you a sample calculation here. I talked about an above ground storage tank, again, a very common CP application. Matcor has systems that we sell for this. Let's take a 200-foot diameter tank bottom. It's just a big crude oil storage tank, 200-foot diameter, okay? Like you'd see around a refinery or a terminal or near an airport where they've got big fuel storage tanks. 200-foot diameter, I chose that because it's nice and easy, because that means the radius is 100. And to calculate the area of a circle, pi r squared. Okay, so we know we've got 31,400 square feet of surface area on that tank bottom that's sitting on a sand base. Okay, well, if we know that I only need 1 milliamp per square foot of bare surface area to protect that tank bottom, and I know I've got 31,400 square feet, I know I need 31.4 amps to protect it. Now, being engineers, we always over-design things, so we'll say, okay, we'll put 50 amps in of capacity. So if I have 50 amps capacity, I know that I can protect that tank bottom. So we talk about current density requirements when we're calculating how much current we need. The current density requirements varies with electrolytes. And being in this business for a long time, and the industry has developed certain current densities that are typically or standard used. For steel in soil that's not really badly corrosive, moderately corrosive soils, 1 milliamp per square foot is good. If it's really corrosive soils, very low resistance, wet soils with lots of salts in them, like you'd get on the Gulf Coast or marshy areas, you might need to go up to 3 milliamps per square foot. If you've got steel in seawater, it might be 10 milliamps per square foot. If it's steel in seawater that's really warm, you might want to go more than that. Okay, so we come up with these guidelines. So it varies depending on the structure. It varies depending on the type of metal you're protecting. Remember I mentioned copper really loves current. You can throw a lot of current onto copper. To protect steel, it takes about 1 milliamp per square foot. To protect copper, it takes about 20 milliamp per square foot. 20 times as much current, because copper loves current. Now, often we don't really care about protecting copper, but if the copper's in the same circuit as the steel, I've got to protect it to be able to protect the steel. So in that case, sometimes if you're in a power plant where they got a grounding grid and you're trying to protect the plant piping and the plant piping is not isolated from the grounding grid, and it's very difficult to isolate the plant piping from the grounding grid, you're going to have to worry about that grounding grid. And that means you're going to probably need a lot more current so that you can feed current to the copper so you can get some current to go to the steel. Then we get into design, we talk about anode selection. This requires a pretty good understanding of how much design life you need, because different anodes consume at different rates. And the quantity of anodes you want to put in is going to be a function of how long you want the anode system to last. If you're building a brand new 200-foot diameter crude oil storage tank, and you know that tank's going to be in service 50, 60, 70 years, and you're going to put a CP system underneath that tank where you can't get there again, once it's built, it's really almost impossible to get back underneath that tank, you're going to want to put a CP system that's designed for 50 or 60 years. So you want to know the design life, a current distribution. Again, that gets into what's the geometry of the structure, where do the anodes need to be located to get current to light up the whole structure, what are my constraints, where can't I put anodes. I'm talking about electrolyte stability. Does the environment change over time? So there's a lot of constraints when it comes to picking what anode to use. One other issue we talk about is anode system resistance. Okay, anodes have a resistance factor based on their geometry largely. Okay, so it's important when selecting an anode to have some idea of how much resistance you need to be able to drive current. I'll go through some of those calculations in a bit, but the key thing there, anode length really drives what the resistance of the anode is. The longer the anode, the lower the resistance of the anode. And we have some equations that we run through. We have an equation called Dwight's equation we use to calculate anode resistance. I'm not going to get into calculating that too much. But as you can see from this calculation here, if I've got a 4-inch by 80-inch graphite anode, it's a standard size for a graphite anode, 4-inch diameter by 80 inches long. It's a pretty long anode. Okay, and I put it in 4,000 ohm centimeter soil. 4,000 ohm centimeter soil is relatively normal soil. Okay, it's not super low resistance, it's not super high resistance, it's a pretty common soil range. If someone told me they had soil and it was not in the desert and it wasn't in the Gulf Coast, in a marshy area, I would use 4,000, 5,000 ohm centimeter soil as just a guess until we had some data. So that's a common soil resistance. That 4-inch by 80-inch graphite, when you run the math, is going to have about 24 ohms resistance, which means to get 1 amp of current off of it, I need 24 volts, because V equals IR. And you can calculate, there's other components to resistance. I'm not going to get too much into the resistance here. I did mention V equals IR. This is a very basic electrical equation. The current that's discharged is a function of the resistance and the voltage applied. Okay? And again, with the galvanic anodes, that V component is very small because I only have that difference between the natural potential of one metal to another. With a power supply, I can adjust the voltage by putting a bigger power supply in. Okay? Design life calculations. I mentioned the hot water heater and the 5-year warranty and 10-year warranties, and they can calculate how long the anode's going to last. That's part of what we do when we design a CP system. We say we're going to need so much current. We design it for so much current. We know the consumption rate of the anode. We can come up with a design life calculation. We can calculate pretty much how long that anode is going to last if it's operated at the conditions we expect it to be operated at. Now, often we design it for 10 amps. They go out in the field. They find out that 8 amps is fine. Well, that's great because now it's going to last longer because I'm not running it as fast. Or you go out in the field and you find out, you know what? It wasn't exactly a 100-foot long sheet pile wall. It was 110 foot long, and it's taking a little more current than we thought it was going to take, and we're going to operate that 10 amp system at 12 amps. Well, that's fine. It'll work in most cases, but it might not last as long as you designed it to. So in this application, that 4-inch by 80-inch graphite I talked about, operating at 3 amps, has a weight of 72 pounds, I'm going to get about 9.6 years life out of that anode. Okay? Is that the best solution? I don't know. That depends on the actual application requirements. Maybe 9.6 years is great, or maybe I put 5 of them in, and now I've got 45 years life. That's part of the design process. So just wrapping up the design basics, CP system design is quantitative, meaning there's things I can calculate. I can kind of calculate how much current I need. I can calculate how long the anode's going to last based on the number of anodes I put in there and how fast each anode consumes. However, the design is also very qualitative. Okay? Why I say CP design is qualitative is because it's one thing to calculate how much light I need to light up the structure for as long as I want to light it up. But there's also the issue of where do I put the lights? Where do I put these anodes to make sure that current's distributing properly to the whole structure? Okay? And that's a qualitative assessment. It's really almost impossible to completely calculate that for every unique application. Some applications it's easier than others, but in many cases it's a pretty complex consideration. there are basically three anode configurations or ways that we place anodes. One is called a remote anode. I'll go into that in detail here. One is called a discrete anode. It's a bunch of individual anodes that are discretely placed in selected locations. And the third way is what we call a linear anode. That's one long anode that runs a long length parallel to the structure you're trying to protect. Just a little terminology here. Ground bed, that's a common term in our industry. A ground bed basically is a place where an anode is located. We talk about shallow ground beds, and we talk about deep anode ground beds. A shallow ground bed generally means it's located close to the surface, 5-10 feet depth. A deep anode ground bed is a ground bed where we might drill down 300, 400, 500 feet and put the anode really deep in the earth so that it'll spread current a long ways. So a remote ground bed system, remote ground beds, we use that term, there's actually something called being electrically remote. If you're far enough away from something, you're electrically remote, meaning that every point of the structure basically is the same distance electrically from the other. I use the analogy of stadium lighting in a football stadium. Okay? When I do these presentations internationally, I have this picture of a cricket field that's lit up, but nobody understands cricket in the United States. But in India, they love cricket, so that's what I use. Or soccer stadium if you're in England or someplace. But the concept's the same. I can light up a football stadium from 3 or 4 lights. 4 lights. Put light stanchion on 4 corners of the football stadium. If they're far enough away and they're high powered enough, I can light up the whole stadium so people can read the newspaper, they can read a book, they can read a playbook, they can play football or whatever from just a few lights. But they have to be really high powered and they have to be far enough away. Okay? Well, we have anode systems that are like that. Our Duramo system we manufacture here at our facility, it's a deep anode system. It's intended to go 300-400 feet down in the ground, and it's intended to kick out a lot of current. From one deep anode location, I might kick out 40-50 amps of current. Okay? It's analogous to stadium lighting. This is a typical deep anode configuration. You got a hole that's drilled in the ground, and then down at the bottom of that hole is an active area where you're going to put anodes, 1 or more anodes into the ground. And those anodes are designed to kick out light. It's a pretty expensive installation, but it's very effective for putting a lot of current out. And if you design it right, it can last a long time. Our Duramo systems are typically designed to last 30 plus years. Key issues with deep anode systems. You can get a lot of output out of them. They're high output systems. Okay? That's not always good. There are some issues with high output anode systems. So it has to be designed properly. You have to use the right materials. You have to use the right construction techniques. You have to put it in the right place. If you have chlorides, naturally occurring chlorides or salts in the ground, part of the reaction that occurs at the anode is you'll generate chlorine gas. Not a whole lot, but you'll generate some chlorine gas. Chlorine gas can attack cabling and cause premature failure of systems. That's why for our Duramo systems, we use a chlorine-resistant Kynar cabling. So there's some issues with it, but that's all part of the design. Current radiates indiscriminately. I put a deep anode system in the ground, current's discharging off of it. Okay? Anything that's electrically connected to the circuit is subject to getting current. And I can't really control where it goes. If I put a deep anode system in a power plant and I've got a network of pipes in the power plant and I've got grounding and other stuff, and they're all electrically connected, I can't control where that current's going to go very well. So I have to have a lot of current to light up everything. Just like my stadium analogy, if I don't have enough current to light the whole place up, I may not have places where there's good light. Commonly used to protect plant environments where I have a real congested underground. Throw a bunch of deep anodes in, you throw a ton of light up, ton of current up in, from these deep anodes up to the surface, and try to protect everything, try to light up everything. They're also commonly used to protect sheet pile walls. The reason for that is sheet pile walls typically aren't coated when they're driven in the ground. You have a large bare surface area, so you start doing the math, you start ending up needing a lot of current. Okay. Plus it's nice, you can put the deep anode system, offset it from the sheet pile wall like I showed in that diagram earlier, put it deep enough, you might be able to protect both sides of that sheet pile wall with just one land-based system. Sometimes you end up putting anodes into the water as well to protect it, it just depends. Often used for long-distance pipelines. Okay. like I said, you put one anode station in, you go another 20 miles, put another anode station in, and they're protecting 10 miles in each direction. Not at all uncommon. Another similar anode to the deep anode system is what's called a remote horizontal ground bed. A remote horizontal ground bed is basically the same thing, except instead of going down, I'm going away. Okay, so if I have a pipeline, I can put a bunch of anodes to create my high-powered remote system, but I have to get it far enough away that it's remote. Okay? So in this case, I might be 1,000 feet away from the pipeline. This basically is a bunch of anodes put together into what we call a ground bed, horizontal shallow ground bed. And now this is, because it's electrically remote, meaning it's this pipeline here, 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 wherever you go along that pipeline is basically the same current distance. Okay, I'm electrically remote. I'll be able to protect a large swath of that pipeline, just as if I drilled down 500 feet and put the anode in the ground that way. Very common in places like up here in the Northeast where we have very shallow bedrock. So many places here in the Northeast, if you go 5, 10 feet, 20 feet into the ground, you're going to hit rock. Okay, rock is not conductive. You don't want to put anodes in rock because nothing will discharge off of them. So there, often they'll put shallow ground beds further away that can generate a lot of current.
Is that our linear anode?
That's where our MMPs are used, our packaged canister anodes. MMPs are used for, correct, that they're commonly used, tubular anodes. Linear anode can also be used for a remote horizontal ground bed. Discrete anode systems. A discrete anode system are a bunch of individually anodes, okay? If we use the stadium lighting analogy, where you've got one high-powered bank of lights protecting a lot, these are like floodlights. They're still pretty high-powered, not nearly as high-powered as your stadium lights. Instead of being 40 or 50 amps, maybe we're talking about 2, 3 amps of current. And you put them, every so many feet, 20 feet, 30 feet, 10 feet, depending on where you space them. And they're spaced around the structure so that you're lighting up the structure from each of these individual discrete lights. Our MMPs, our canister anodes, are used for this purpose as well. Okay? And typically they're put in at 5 to 10 foot depth. So you can take an auger, you drill a hole 5 or 10 foot deep, you drop the anode in the hole, you go on some distance away, you put another one in, and another one, until you've got enough of them to protect the structure.
Now, do those all connect to each other?
You can connect them all together in one string, or you to one rectifier, or you can connect them to a junction box and power the junction box from that rectifier. But ultimately, they would all get connected to one or more rectifiers. If you've got enough of them spread around a large facility, you may have multiple rectifiers powering banks of these discrete anodes. The issue with discrete anodes, just like spotlights around a house, is where do I put them and how do I make sure that they're spaced so that I'm getting current everywhere, okay? Because if I don't put the lights in the right place, there might be areas that aren't getting current. And that's more of an art than a science. In fact, if you take the same application and give it to 3 different CP designers, you're going to get 4 different designs, okay? Because everyone's going to space them a little differently, place them a little differently. There's no right answer. It either works or it doesn't work, okay? So there's a right answer. There's no one right answer. And that's why when you do these discrete anode systems, it's really important to go back after the fact and test them. It's important to do that for any system, but discrete anode systems especially. The other issue with discrete anode systems, and here's just a little diagram of a discrete anode. In this case, it's a galvanic anode. It's a hunk of magnesium installed next to a piece of pipe. It's protecting some area of that pipe. It's not going to protect everywhere of that pipe because it's close enough. It's like my flashlight analogy. It's only going to protect a certain amount of that pipe. It's runs up to a test station so I can test it. That's what that galvanic anode looks like. It's a hunk of magnesium. We stick it into a sack that's filled with a backfill material, and you bury it next to the structure you're trying to protect. Do the same thing with an impressed current anode. That's also a discrete anode. Now you're going to run a cable to a power supply and use the power supply with all the advantages the power supply has, a volume switch so I can turn it up and down. I can generate more current off of it. This is our mixed metal oxide canister anode. Great anodes, lightweight, low cost, easy to install, very long life, quite robust as a discrete anode. Here's a diagram of a discrete anode system. Imagine this as being a simple power plant or maybe a gas line system going to a housing development, okay? You got a main line coming in, and you got little trunk lines coming off, and you want to protect that, so you space anodes. Okay? How many anodes you need, how far apart they are, that's a design issue. Some designer is going to sit there and say, I think I need them this far apart, and hopefully they get it so that you're getting current, enough light everywhere you need it to go. So that was discrete anode systems. So we went from high-powered to medium-powered. Now we're going to talk about really low-powered systems. A linear anode system is like fiber optic lighting. Anyone ever play with a fiber optic light? You can put your hand around it. There's no heat coming off of that light. It's very low power, okay? Very low intensity. That's what a linear anode is analogous to. It's like fiber optic lighting. They have some significant advantages over discrete anodes because now I just place the thing parallel to the whole structure and I know I'm closely coupled to it. I'm very low output, but because it's closely coupled, I'm going to be protecting everywhere that anode goes. I like to use that light analogy of fiber optic lighting. You see in this swimming pool picture here, one little fiber optic light all around the perimeter of that pool lights the whole pool up really nice. Linear anodes work the same way. If you recall that picture of the pipeline system where I had to decide where to put the anodes, in this case, it's almost foolproof design. I'm putting the anode right parallel to the pipe. Wherever the pipe goes, the anode's right next to it. If the anode's properly sized, it's going to light up that pipe. Okay? We use this a lot for power plant projects and plant piping projects for new construction. New construction compressor stations where they're putting piping in the station. Great design, because as they're putting the pipe in, you just put the anode parallel to it. Okay? In China, on the West-East gas pipeline, one of the largest pipeline projects going on in the world, actually they're on phase 3 now, they've got thousands and thousands of meters of linear anode on compressor stations following pipe, just like it's shown here. There's a lot of advantages to this from a CP design system. One, you know that wherever the anode is, that pipe that's close to it is getting current. And it also is extremely long life. These linear anode systems, they'll have a design life of 50 to 100 years easily because they're not putting out a whole lot of current, especially with well new coated pipe. Here's a picture of a linear anode installation. You can't really see him, but way in the back there was Glenn Schreffler, our engineering manager. This is a power plant project in New Jersey. Quick story, I think I have a few minutes left. This was the power plant they were building, and they said, we want to put a deep anode system in. Stadium lights. We want to put a deep anode system in to protect this one gas line that's going to run around the whole plant. Everything else in the plant is plastic pipe. We do have copper grounding systems, so we know that we're going to have to put a lot of current into the ground because the copper is going to suck up some of it. And we said, great, we can put the deep anode system in, but then you're going to have to test it. And if there's some areas, because again, I don't really control where current's going with the deep anode system, if there's some areas of that pipeline that aren't getting enough current, we may have to put some more systems in. And we asked the question, have you built the pipeline yet? Oh, we're in the middle of getting ready to construct it right now. They're getting ready to lay it in. We told them, well, we manufacture this linear anode product. I could have that to you in 3 days before you backfill the pipe. If you just lay it parallel to your pipe, you don't have to worry about, am I getting current where I need to go? And it's going to be cheaper. This is a great application for new construction because the cost to install is very minimal. It's just a couple of laborers basically reeling out this anode, putting it parallel to the pipe. And the design certainty is fabulous. That's the end of my presentation on cathodic protection.